Today, we're creating a P chart from start to finish. When your sample size changes from batch to batch, this is the control chart you reach for, and it's one of the essential tools for monitoring attribute data. We'll do everything hands-on inside the SIGMADESK Control Chart Generator because the best way to learn these tools is to actually use them. And don't worry, we'll cover the theory as well. If you'd like to build a chart along with me, go ahead and create an account. You'll find today's sample dataset in the description below. From the home page, I head to the Applications menu and select Control Chart for Attributes, which opens a simple interface. Getting data in works in two ways. Paste your dataset straight into the spreadsheet or bring back a control chart you saved earlier. This time, let me load a saved chart again. In the Chart Options section, I select my saved study and load it. Everything you build here can be saved and reopened later, so nothing gets lost. And here is our P chart, drawn on the screen. Before we go further, let's look at the spreadsheet for a moment in case you want to paste your own data. The layout is the same as before. The first column contains the labels that appear along the x-axis. The second column is the number of defective units in each sample. And the third column is the sample size. But notice the difference this time. The values are not identical. They change from row to row, and that is exactly the point of the P chart. Unlike the NP chart, the sample size does not need to be constant here. I will make this clearer now. Before we start reading the chart, let's take a moment for the theory behind the P chart. If you want to skip the theory and formulas and go straight to seeing this in action inside SIGMADESK, you can jump to the timestamp on your screen. What happens when you cannot hold the sample size constant? Maybe you inspect 100% of daily production and production volume changes every day. In this case, raw counts are no longer comparable because 5 defectives out of 90 units is worse than 5 defectives out of 110. This is where the P chart comes in because it handles varying sample sizes. Here's our data set on screen. Over 10 days, we inspected daily lots, but this time the sample sizes range from 90 to 110 units. In total, we inspected 1,000 units and found 50 defective units. On day 1 specifically, we inspected 100 units and found 5 defectives. The plotted point on a P chart is the proportion defective for each subgroup, which equals defectives divided by units inspected in that subgroup. For day 1, that is 5 divided by 100, which is 0.05, and we calculate this proportion for every day. The center line is P bar, and the formula total defectives divided by total units inspected. Applying it, P bar equals 50 divided by 1,000, which is 0.05. Note that we do not average the 10 daily proportions, because that would give equal weight to subgroups of different sizes. Always divide the totals. Now the control limits, and here is where the P chart differs. The formula is P bar plus or minus 3 times the square root of P bar times 1 minus P bar divided by N. Notice that N, the subgroup sample size, appears inside the formula, which means each subgroup gets its own limits. Applying it to day 1, where N was 100, we get 0.05 plus or minus 0.0654. So the upper control limit for day 1 is 0.1154 and the lower limit comes out negative, so we set it to 0. You repeat this limit calculation for each day using its own sample size, and with that, this is our complete P chart. The limits step up and down as the sample size changes. With SIGMADESK, you never have to work through these formulas yourself. So let's return and look at our real example. Our dataset contains 25 samples, and the sample size varies from batch to batch, roughly between 100 and 150 units, with an average of about 127 as you can see here. This is exactly the situation the P chart was designed for. The center line sits at 0.057, meaning on average about 5.7% of our units are defective. And look closely at the control limits. They are not straight lines. They stair-step up and down from point to point because each sample has its own limits calculated from its own sample size. Smaller sample groups get wider limits, larger samples get tighter limits. The statistics panel shows the limits based on the average sample size, with an upper limit of 0.119 and a lower limit of 0. Now notice the red points. 3 samples fall outside the control limits, all of them above the upper limit. Sample 9, sample 17, and sample 21. Something clearly went wrong in these 3 batches, and in a real investigation, they would be our starting points. Perhaps a machine drifted, a material law changed, or a new operator took over. So that's the P chart, the flexible companion of the NP chart we covered earlier. If you want to keep practicing, the tool is waiting for you at SIGMADESK. And remember, you can also build all the other control chart types along with quality tools like Gauge RNR, capability analysis, and more. If you found this video helpful, consider the like button as a simple thank you. Subscribe for more Six Sigma content, and I'll see you in the next video.